there, everybody. I want to take a minute to talk through this DEM download lab and show you some of the differences between the data sets, and I'll also attach another one that talks in more detail about how they're constructed. But I kind of want to talk about the visuals, and then I'm going to take a quick look at the discussion board and just show you some of the issues that come up. And this isn't to pick on anybody. This is the kind of stuff that happens to all of us all the time. The nice thing about the discussion board is it gives us an opportunity to look at all the different ways we can display hillshades and elevation models, and it gives you an idea of things that really appeal to you, things that look really effective, and how to troubleshoot issues that come up with hillshades and resampling techniques. So what I'm showing you here are the three data sets side by side. I just created three different data frames. One's got a 2-meter elevation model and then corresponding hillshades, and same with the 5-meter and 10-meter. So again, this is the LiDAR data set, and you can clearly see its ability to pick up a lot of very fine details, and we get a solid lake surface or reservoir surface elevation, which we get a little bit in the 10-meter data from the National Elevation Data Set, but really looks like puddled mercury in the 5-meter data set. And so like I said, check out this other video that talks about how these data are built, how these elevation models are constructed, because that gets into a lot of this nuance that we see between the three and the level of error that we see with the autocorrelated DEMs. These are made back in the olden days, literally looking at stereoscopic images taken when vegetation is at its peak and full leaf on conditions, and then looking at three-dimensional photographs through stereoscopic goggles, and then trying to interpolate the surface from that. And so we do end up in heavily vegetated areas, end up with interpolated surfaces that are completely false, best estimates, and then at the very best, we just get kind of a bumpy, still somewhat erroneous surface. As far as error goes, even though the resolution is so much lower, the 10-meter data set is going to be more accurate than the 5-meter in almost every single case. And by 5-meter, I mean autocorrelated. It's not the resolution, it's the way that it's constructed. Okay, the second thing I want to demonstrate is what happens if you put a color ramp on your hillshade. Hillshade, you can tell it's a hillshade whether you've labeled it correctly or not, because the range of values is 0 to 254. And unless you happen to end up with an elevation model that has a range of values from 0, sea level, to 254 meters above elevation, this should be very easy to spot. The color ramp on a hillshade should always be black to white, with white at the top for the high values here. When you put a color ramp on hillshade, you lose that three-dimensional look. So all you're seeing here is just the raw hillshade. I can put a transparent elevation model on top to try and exaggerate the look of the elevations and add that information in. But when we bring in color ramp on a hillshade, you end up modeling everything, and it gets this very science fiction-y weird look to it, and you lose that three-dimensional surface. So I'm going to turn off the hillshade that's got a color ramp on it, and the terrain pops back into view. So this is just a rule of thumb that you need to wrap your head around. Color can go on an elevation model, absolutely. So when you see elevation values, but on a hillshade it needs to stay black to white, and that's why, because you just lose it. So with the 5-meter I can do the same thing. I can put on a little bit of color here, but then if I turn on my hillshade that has color, it just washes everything out, and you lose that terrain, the three-dimensionality. And with my 10-meter, I haven't set up the same thing here. Actually, what I want to demonstrate on the 10-meter data set is the gridding pattern and where that comes from. And so the raw data that you got from the USGS comes in a geographic coordinate system. And if I look at the properties, my cell size is very, very small. If I scroll down, my extent is showing very small values. This should indicate to you that this is latitude and longitude. These are angles, so they're less than 180 degrees absolute value, and that's the angle from the center of the Earth out, north 41 degrees north of the equator, 39.9 degrees north of the equator. That's the extent of the data set, but this indicates that it's in a geographic coordinate system. This also indicates that it's in a geographic coordinate system. It's the North American datum of 1983, and the units are angular degrees. This is latitude and longitude. The vertical scale has been measured in meters. That isn't necessarily related to these, but it is almost always reported in meters, elevations. But this has more to do with the measure of the vertical datum. We don't have to worry about that too much. So, yeah, the point here is that you need to project this data. I wasn't able to recreate the look that you get when you work with a geographic coordinate system and create a hillshade, but some of you were able to get that, and I'm just gonna, this one it depends on where you are in the watershed. This one starts to get at this really exaggerated shadowing. I suspect that this was a hillshade that was created from the raw data that came in from the USGS without projecting it to a UTM coordinate system. These look really good. This one is another example of that extreme shadowing that you get where you really can't make a good comparison here because the shadows are so black that you kind of lose the data. And so I suspect this one also wasn't projected before the hillshade was calculated. These all have a very comparable lightness to the surface, if you know what I mean. I think there was a couple more up here. This one has that heavy shading. And then this one is an example of color on the hillshade. So a couple of you made a comment that it was very hard to see the differences between these two, and that's for this same reason, that you've got color on the hillshade. So that's just a live and learn, and then remember to keep your hillshades black to white. Okay, so what I'm looking at, what I just showed you here, were the properties for the 10-meter data in a geographic coordinate system. And when we go ahead and let me put a color ramp on this. I went ahead and ran the project raster tool and transformed this from a geographic coordinate system to the UTM, or a projected coordinate system. Let me throw the same color ramp on there for consistency. Normally I would flip this. So I'm so far zoomed in that you really don't even get a sense of the landscape here. I will make it semi-transparent at the same time. And that lets us see our hillshade a little bit. But again, if I put a color ramp on this thing, we're going to lose that entirely. So symbology, putting color on a hillshade, big no-no. But at least we get kind of a consistent look. It just flattens everything out. And I know I'm repeating myself, sorry. So let's turn on this other one. And I want you to see this gridded pattern that appears in here. Now, the data from the Utah AGRC, I made a comment about this in the instructions, that for the longest time, the 10-meter data that you could download and the 30-meter came in with this hatching pattern. And it's because when they ran the project raster tool, they didn't change the resampling technique to bilinear. So this is the project raster tool. You put in your geographic coordinate system, you tell it you want it to be UTM in our case. The resampling technique that says optional is not optional. You have to change this to bilinear interpolation or cubic convolution, but for elevations I recommend bilinear. The cubic convolution, you can end up with values that exceed your minimum and maximum. And with the bilinear, you get more of a smoothing effect, and you're not going to get values that exceed your min and max elevation values. That's why I recommend this one. But the nearest neighbor, it says right in the tool help that this is good for discrete raster data like land cover. So raster data sets that don't have continuous numeric values like slope, wind speed, solar radiation, but instead are representing categorical things like trees versus lake versus wild grasses, or soil type clay versus soil type loamy silty sand. So categorical things should be resampled with the nearest neighbor resampling technique, but our elevations need to be switched to bilinear. And so the Utah AGRC and all of us for a long time, because we ignored that nearest neighbor optional setting, ended up with projected elevation models that had this icky gridding pattern. You can't fix it in the hillshade. You have to go back, and this is actually in the hillshade that you see it. It is technically also in the elevation model. You just can't see it until you create the hillshade from it. But once you fix that, you end up with a nice clean one. You have to go back and project the elevation model again and then rerun your hillshade to clean that up. And I'm just going to change this back to the black to white. And if you just remember, you can invert it this way, but you want the white to be at the top. Okay, so that's kind of the visual display of DEMs and hillshades in a really huge nutshell. I welcome you, please, to watch this other one where we talk about the creation of elevation models. And if you have any questions about this, let me know. Thanks.